The planet Earth is not stationary at this very moment. You are, in fact, rotating at a velocity greater than 1,670 kilometers per hour, while simultaneously speeding around the Sun at a rate of nearly 108,000 kilometers per hour. Every single sunrise you have ever observed was not, in truth, the Sun moving. It was you. It was the planet itself, silently rotating to greet the light. This evening, we intend to slow down our perception of time and carefully trace that complex motion. We will follow it from the specific inclination of Earth's axis all the way to the concealed tempo of its orbit, aiming to comprehend how every moment of your existence is fundamentally authored by movement. If this tranquil exploration provides you with even a brief interval of serenity, I am profoundly thankful that you are here to share it. A simple like or a soft click on the subscribe button greatly assists me in continuing the creation of these nocturnal voyages. Now, let us commence with the primary truth. Part 1. The Sun is stationary. The Earth rotates. With every second that elapses directly beneath your feet, the ground is turning. It is continuously carrying you in an eastward direction faster than the very speed of sound. You do not perceive this motion, and yet it never ceases. Every wall in your home, every sprawling city, every vast ocean, all of it is in a state of constant rotation through space at 1,670 kilometers per hour around the planet's central axis. Simultaneously, the entire Earth is hurtling in its orbit around the Sun at a velocity approaching 108,000 kilometers per hour. What this implies is that even when you are sitting in a state of perfect stillness, you are actually traveling tens of thousands of kilometers with every single hour that passes. And despite this, it feels as though you are not moving at all. That profound illusion, the absolute stillness of immense motion, stands as one of the most remarkable phenomena in the entirety of physics. It is the quiet, underlying reason that the Sun appears to rise in the morning and set in the evening, even though, in reality, the Sun remains stationary. Each new dawn is not a sign of the Sun returning to us. Rather, it is the signature of our own world gently pivoting once more toward the light. The Earth completes one full rotation every 23 hours, 56 minutes, and 4 seconds, which is just shy of a complete 24 hours. Astronomers designate this specific duration as a sidereal day, which is measured by determining how long it takes for the planet to execute one complete spin relative to the far-distant stars. The 24-hour day that we structure our lives around is marginally longer. This is because while the Earth is rotating, it is also traveling along its orbital path. Consequently, it must turn just a little bit further each day for the exact same location on its surface to face the Sun once again. That minuscule variance, amounting to only 4 minutes, subtly reshapes the appearance of the sky every single night. Over the span of 1 month, those 4-minute increments accumulate, adding up to 2 full hours. Within a year, they accumulate into an entire day. This means that the stars gleaming in the sky above you tonight are not situated in the identical positions they occupied during the last season. They have perceptibly shifted, not because the cosmos has moved, but because you have. Our ancestors recognized this celestial drift long before the advent of satellites or atomic clocks. They diligently observed the changing lengths of shadows cast by the Sun and meticulously recorded the slow migration of the constellations. The ancient Egyptians, for example, constructed their temples with such precision that sunlight would illuminate a single, specific point within the structure only once per year, a cosmic alignment purposefully encoded into solid stone. Today, NASA confirms these very same rhythms by employing a technique known as very long baseline interferometry. This method involves comparing radio signals received from distant quasars to precisely measure Earth's rotation, achieving an accuracy that is within a fraction of a millisecond. However, this rotation is not perfectly uniform. Atmospheric winds shift, ocean currents move, and massive glaciers melt. Each of these events redistributes the planet's mass, which in turn slightly modifies its rotational speed, much like an ice skater who alters their speed of rotation by pulling in their arms. Following significant earthquakes, NASA's Jet Propulsion Laboratory has documented measurable alterations in the planet's rotational period, sometimes changing by only a few microseconds. That extraordinary precision, that inherent stability, is precisely what makes life on this planet possible. The rotation of the Earth balances global temperatures, it drives the powerful jet streams, and it shapes the worldwide daylight cycle that dictates the behavior of every ecosystem. Without this motion, our world would be an unrecognizable place. Carl Sagan famously stated, "The Earth is a very small stage in a vast cosmic arena." He was entirely correct. But it is also a stage that is in perpetual motion, endlessly spinning while governed by the invisible laws of angular momentum, laws that connect us to every other rotating object throughout the entire universe. From the smallest electrons to the most massive galaxies, spin is one of the most fundamental and universal patterns found in nature. Consider this. At this precise instant, your physical body, the air surrounding you, and even the very atoms that constitute your bones are all traveling with the exact same velocity vector. This is the reason you do not feel the motion. Everything that is relevant to your existence moves in perfect unison. It is a flawless synchronization, perhaps the most elegant example of inertia that can be personally experienced. If the Earth were to abruptly cease its rotation, even for a single second, every object not physically anchored to the planet's crust would violently continue its eastward trajectory at over 1,670 kilometers per hour. Oceans would surge across the continents, cataclysmic winds would rip the surface apart, and the planet's delicate equilibrium would utterly collapse. This is, of course, a theoretical scenario, one studied by geophysicists to better comprehend how rotational energy is fundamental to the stability of worlds. Through the data collected by the Gaia mission, scientists have also observed that our planet's axis experiences a slow wobble. This phenomenon is known as axial precession, and it completes one full cycle every 26,000 years. This gradual shift systematically alters the orientation of Earth's poles and even determines which star we designate as the North Star. Thousands of years ago, the North Star was not Polaris as it is today. It was a star named Thuban, located in the constellation Draco. Therefore, even our most basic definition of north is only temporary. Everything we perceive as fixed, our sense of direction, the arrival of daylight, the very concept of a day itself, is merely the result of motion layered upon motion, layered upon motion. And yet, existing within all of that immense complexity, there is something profoundly soothing. It is the fact that in all of this movement, the Earth remains stable enough for us to live, to breathe, and to sleep. The very same laws of physics that propel us through the vastness of space also shelter us within a state of balance. So when you awaken to the morning light tomorrow, remember, the sun did not rise. You did. The planet beneath you never stopped turning. And yet, it never travels at the exact same speed twice. As it journeys through space, Earth accelerates and decelerates, tracing an invisible path that changes every single day of the year. And as we continue this quiet journey, one question lingers. Part 2. Why does the sun seem to speed up and slow down during the year? Have you ever perceived that the sun does not maintain perfect time? On some days, it seems to rise a few minutes earlier than it is supposed to. At other times, it appears to linger in the sky, setting later than anticipated. Even the most precise clock ever constructed cannot perfectly track the sun because the sun itself appears to alter its pace across the sky. But the truth is, it is not the sun that is changing its speed. It is the Earth. Our planet does not orbit the sun in a perfect circle. Instead, it follows an ellipse. This is a slightly stretched out or elongated path, which was first accurately described by Johannes Kepler in the year 1609. According to Kepler's second law, often referred to as the law of equal areas, a planet invariably moves faster when it is closer to the sun, and it moves slower when it is farther away. In the month of January, Earth reaches what is called perihelion. This is its closest point to the sun, situated approximately 147 million kilometers away. Conversely, in the month of July, it reaches aphelion, its farthest point, at a distance of about 152 million kilometers away. That relatively small difference of just 5 million kilometers changes absolutely everything about the rhythm of our sky. When the Earth is near perihelion in January, its orbital speed accelerates to approximately 30.3 kilometers per second. 6 months later, when it reaches aphelion, it decelerates to roughly 29.3 kilometers per second. This 1 kilometer per second variation might appear minor, but when extended across millions of kilometers, it fundamentally reshapes the apparent motion of the sun as we observe it from Earth. It causes our days to subtly stretch and contract in measurable ways. Astronomers refer to this effect as the equation of time. It stands as one of the most quietly fascinating corrections in the field of celestial mechanics. It is a mathematical formulation that explains why solar time, time kept by the sun, and clock time, time kept by our devices, are never in perfect alignment. If you were to attempt to measure time purely by the sun's position, that is, by the true moment it crosses the meridian directly above your head, and then compare that observation to your watch, you would discover a small but persistent discrepancy. Sometimes the sun is running ahead of the clock, sometimes it is lagging behind. Over the course of a full year, that difference can accumulate to as much as 16 minutes. This variation occurs for two principal reasons. First, Earth's elliptical, non-circular orbit, and second, the tilt of its axis. The axial tilt causes the sun's apparent speed across the sky to change throughout the seasons, while the elliptical shape of the orbit changes Earth's actual velocity. When combined, these two factors make the solar day, the duration of time between two successive noons, slightly longer or shorter than a standard 24 hours. In early January, when we are moving at our fastest speed around the sun, each solar day lasts a fraction longer than the average. Around early July, when the Earth moves at its slowest, the solar day is marginally shorter. This difference can be as much as 30 seconds per day, which then accumulates into noticeable shifts as the months progress. This is precisely why sundials, which are ancient yet remarkably accurate timekeeping devices, do not always match the time displayed on your phone's clock. The sun does not adhere to human definitions of time. It moves according to the laws of physics, not by the design of calendars. NASA's Solar Dynamics Observatory, or SDO, meticulously tracks these changes by recording the sun's apparent motion against the backdrop of the celestial sphere. When scientists plot that specific motion, day by day, throughout an entire year, the sun's position traces a graceful figure-8 pattern in the sky. This pattern is known as the analemma. You can sometimes see this shape depicted on older world globes, usually as a slender loop situated near the Pacific Ocean. It is shaped by both Earth's axial tilt and its varying speed in orbit. That figure-8 is, in essence, a map of imperfection. It is a visual signature of how our planet's motion is slightly unbalanced, slightly off-center, and yet beautifully predictable. It informs us that time itself is not a constant, steady rhythm, but rather a direct reflection of motion. In December and January, when the Earth is racing around the Sun at its maximum velocity, the Sun appears to lag behind our schedule, crossing the meridian later and later each day. In March and September, the Sun's apparent position catches up. These oscillations are the reason why the earliest sunset and the latest sunrise do not occur on the solstice itself, but rather weeks before and after it. The equation of time quietly clarifies why the longest day of the year, the summer solstice, does not coincide with the earliest sunrise. The European Space Agency's Gaia mission and NASA's JPL Horizon system are now capable of calculating these orbital variations with extraordinary precision. The data they provide confirms that Earth's speed and distance shift predictably every single year. It also confirms that even subtle gravitational tugs from the Moon and the other planets contribute tiny, measurable deviations to this rhythm. When those gravitational tugs align in just the right configuration, the planet's orbit subtly breathes, a cosmic inhalation and exhalation that has been repeated every year for billions of years. And yet, despite all of this complexity, the daily difference is something you can actually sense without needing scientific instruments. If you have ever looked up on a dark winter morning and felt that the light was arriving later than you expected, you have already sensed the equation of time at work. It is the invisible clock of the cosmos, the one that never tells a lie, but also never repeats itself exactly. As the physicist Neil deGrasse Tyson once remarked, "The universe is under no obligation to make sense to you." The sun's uneven motion is a quiet reminder of that fundamental truth. What feels irregular or inconsistent to us is, in fact, perfectly lawful, meticulously shaped by geometry, gravity, and angular momentum. So, why does any of this matter? It matters because it demonstrates that time, even the kind that is ticking away on your wrist, is not absolute. It is constructed upon the foundation of motion, and motion itself changes based on distance and speed. The equation of time serves as the bridge between human-defined time and solar time. It connects our innate need for order with the beautiful chaos of celestial mechanics. It is also a perfect illustration of how precision in the field of astronomy has evolved. In the 18th century, navigators navigating the open seas relied heavily on this knowledge to determine their longitude. They would compare the observed position of the sun in the sky with the expected mean solar time. A discrepancy of only 1 minute could translate to a positional error of about 28 kilometers. This is why John Harrison's invention of the marine chronometer in the year 1761 changed navigation forever. It finally allowed human beings to measure time with the accuracy required to safely traverse the world's oceans. Today, the atomic clocks situated aboard GPS satellites depend on even finer corrections. They must account not only for the equation of time, but also for the profound effects of general relativity. This is because time itself actually flows at different rates depending on altitude and velocity. Without making these precise adjustments, GPS locational errors would accumulate at a rate of 10 kilometers every single day. So, when your phone provides you with the exact time, it is actually combining the theoretical work of Einstein, the laws of Kepler, and centuries of meticulous celestial observation. All of that effort is expended just to synchronize your heartbeat with the complex motion of a spinning, orbiting planet. The next time you happen to glance at a clock and notice that the sunset seems to be off by a few minutes, remember that it is not your clock that is incorrect. It is simply the Earth, faithfully keeping its ancient elliptical rhythm. The equation of time is far more than a mathematical curiosity. It is a direct reflection of our planet's imperfect perfection. It is definitive proof that the natural world never truly repeats itself, and that even the most stable, reliable cycles contain hidden, subtle variations. So tomorrow, when the sun rises, but not exactly when you expect it to, take a quiet moment. You are bearing witness to one of the most delicate and intricate balances in all of celestial motion, the complex result of gravity, geometry, and time, all intertwined. And as we continue to trace that delicate balance through the changing seasons, one question naturally follows. If time itself is capable of bending and stretching with motion, then what exactly are we measuring when we measure a day? Because if all of our clocks are dependent on Earth's imperfect spin, then perhaps what we refer to as time is only a shadow and not the truth itself. Part 3. Does true time really exist? Here is a strange and unsettling fact. There is no single, universal moment that is shared by everyone in the universe simultaneously. Even this very second, the one you are experiencing as you listen, does not occur at the same time for everyone, everywhere. The faster you move, or the stronger the gravitational field you are in, the slower your clock runs when compared to mine. This is not a philosophical proposition. It is a physical reality. When we, as a species, made the decision to measure time using mechanical clocks instead of observing the sun, we unknowingly diverged from the natural inherent rhythm of our planet. For thousands of years, the passage of a day signified one complete rotation of the Earth, one sunrise, one sunset. But as our scientific instruments became progressively more precise, we uncovered something deeply unsettling. Nature's time and human time are not the same thing. In the realm of classical mechanics, time was considered absolute. It was believed to flow everywhere at the exact same rate, independent of everything else. That conception worked perfectly well for Isaac Newton, who wrote, "Absolute, true, and mathematical time of itself, and from its own nature flows equitably without relation to anything external." But in the year 1905, Albert Einstein completely shattered that certainty. Einstein's special theory of relativity revealed that time is not an independent background force. Instead, it is woven together with space into a single unified structure known as space-time. According to his revolutionary equations, time only possesses meaning when it is compared directly to motion. The faster an object moves through space, the slower its time passes relative to a stationary observer. This effect, which is called time dilation, is now one of the most rigorously tested and confirmed predictions in all of physics. In the year 1971, scientists named Haffel and Keating conducted an experiment where they flew atomic clocks aboard commercial airplanes, traveling both east and west around the Earth. When they returned, they compared those clocks to identical ones that had been left stationary on the ground. They found that the flying clocks were out of sync by mere billionths of a second, an amount that matched Einstein's predictions exactly. Today, this very same correction is vital to the successful operation of the Global Positioning System, or GPS, satellites. Each of these satellites orbits the Earth at a speed of about 14,000 kilometers per hour. Consequently, their onboard clocks actually tick slightly faster than clocks on Earth because they are farther away from the planet's gravitational pull. Without actively applying Einstein's equations of relativity, the GPS system would accumulate errors resulting in a drift of 10 kilometers every single day. So, when your phone tells you precisely where you are, it is quietly utilizing general relativity to make sense of the relationship between time and motion. Modern physics pushes this concept even further. In the framework of general relativity, time itself is shown to bend and warp around massive objects. The stronger the gravity, the slower the passage of time. If you were near a black hole, mere seconds, for you could stretch into entire hours for an outside observer. NASA's Event Horizon Telescope confirmed this principle in the year 2019, when it successfully captured an image of the shadow of the supermassive black hole in the galaxy, M87. This is a region where gravity distorts both light and time so profoundly. Einstein described this intricate relationship as being simple yet profound. Mass dictates to space-time how it should curve, and in return, space-time dictates to matter how it should move. The ultimate result is that time flows at different rates in different parts of the universe. As NASA clarifies, clocks run slower when they are near something massive, and they run faster the farther away you are from it. Therefore, what we call a second is merely a local phenomenon, valid only here on Earth, existing under our planet's specific gravitational field and rotational speed. Somewhere else in the cosmos, that very same second is either longer or shorter. There is no single cosmic clock that is ticking universally for everyone. Within the realm of quantum mechanics, the problem of time becomes even stranger. At the subatomic scale, time does not appear to behave continuously. Particles do not follow smooth, predictable trajectories. They exist instead as fields of probability, where time itself seems to pause between distinct interactions. Experiments conducted at CERN and other advanced laboratories suggest that time, much like matter, might actually emerge from deeper, more fundamental physical laws, not as a fundamental property of the universe, but perhaps as a statistical one. If all motion in the universe ceased, if every atom, every photon, and every planet stopped moving, the equations of physics tell us that time itself would vanish. This is because time, in its purest and most fundamental form, is defined by change. It is not a thing that exists independently. It is, instead, a measurement of how one state transforms into another. The European Space Agency's Gaia mission has provided one of the most precise temporal frameworks ever created by humanity, a cosmic clock that is based on the motions of over 1.5 billion different stars. Even then, the data clearly shows that everything, from the largest galaxies to the smallest subatomic particles, exists in a state of continuous, relentless motion. There is no such thing as absolute stillness anywhere in the cosmos. This means that the very idea of true time, a single, universal now, does not exist. Every individual point in space possesses its own unique version of time, inextricably linked to its velocity and its gravitational environment. Astronomers refer to this as proper time, which is the time experienced by an object within its own frame of reference. On the International Space Station, for instance, astronauts orbit the Earth every 90 minutes, traveling at 7.8 0.66 kilometers per second. Their clocks tick approximately 0.01 seconds slower for every 6 months they spend in orbit compared to the clocks running on the ground. The difference is minuscule, but it is real. When they return to Earth, Mission Control must adjust their recorded time to match Earth's reference frame. The most accurate clocks ever constructed by humans, known as optical lattice clocks, are so sensitive that they can detect the difference in the passage of time between 2 points separated by just 1 centimeter in height. At that astonishing level of precision, the simple act of standing up means that your head is aging infinitesimally faster than your feet. As NASA physicist Don Lind once aptly put it, everywhere is local time. This is not just a theoretical curiosity. It represents a fundamental shift in how we must comprehend reality. Time is not a river flowing independently outside of us. It is a dimension that actively changes its shape in response to motion and mass. It is flexible, it is elastic, and it is deeply connected to energy itself. If you could somehow freeze the motion of every single particle in the universe, every photon, every wave, every oscillation, time would stop. There would be no before or after, no aging, no sequence of events. The entire universe would become a single, unchanging snapshot. But the universe cannot stop. Motion is the very fabric of existence. Time exists only because everything moves. This is why, in physics, time is inseparable from space and energy. Einstein's field equations do not treat time as a passive background variable. It is an active component of space-time curvature. When physicists at NASA and ESA run simulations of cosmic evolution, they do not simply run time forward. Instead, they compute how the density of energy changes and shapes the universe. Time is simply what that change looks like to an observer embedded within that system. Even the James Webb Space Telescope, or JWST, operates as a kind of time machine. This is not because it manipulates time, but because light itself carries time within it. When the JWST observes a galaxy that is 13 billion light-years away, it is actually seeing the light that departed from that galaxy 13 billion years ago. In other words, telescopes do not look through space. They look through time. Every photon is a timestamp. Every wavelength is a detailed record of motion, energy, and decay. When we observe the cosmos, we are not merely watching something out there. We are, in fact, reading the archive of time itself. So, does true time exist? The answer, according to every modern experiment, is no. Not as an independent, self-sustaining entity. Time is not universal. It is relative, it is local, and it is entirely dependent on movement. That realization fundamentally changes how scientists build models of the universe. The equations of cosmology are written in terms of space-time intervals, not moments. Even our concept of the age of the universe, which we state as 13.8 billion years, is an age measured specifically from the reference frame of the cosmic microwave background. It is not an absolute age that applies everywhere. Neil deGrasse Tyson summarized this concept simply. The universe doesn't care what time it is where you are. For the vast majority of human history, we believed that time was something external for us to measure. We now know that time is something we generate, through our motion, our gravity, and our observation. And that, perhaps, is the most humbling discovery of all. The flow of time is not an external rule imposed upon the cosmos. It is the dynamic, ever-changing consequence of everything that moves within it. Tomorrow, when you happen to glance at your clock, consider this. The seconds you are observing are not fixed. They are intrinsically tied to your planet's rotation, to your altitude above sea level, and to your motion through the fabric of space. Every single tick is a reflection of precisely where you are in the universe. And in the next chapter, we will follow that ticking clock even deeper to understand how the concept of noon itself changes from one place to another, and why even the idea of midday is not the same for everyone, even for those living under the very same sun. Part 4. Noon is not the same everywhere on Earth. At this precise moment, somewhere in the world, it is exactly 12 o'clock noon. But at that location, the sun is not directly overhead. In fact, for the vast majority of places on Earth, the sun is almost never directly overhead at 12 p.m. The clock on the wall may indicate that it is midday, but the sky itself says otherwise. This small but persistent mismatch between what your watch tells you and what the sun is actually doing is one of the most commonly overlooked consequences of how our planet spins and tilts on its journey through space. It also serves as a window into how human beings gradually and systematically replaced natural time with artificial time. The true physical definition of noon, known in the field of astronomy as local apparent solar noon, is quite simple. It is the exact moment when the sun crosses your local meridian. That is, the invisible north-south line that runs directly through your specific location. At that precise instant, the sun achieves its highest point in the sky for that particular day. At that moment, shadows are at their absolute shortest. But because the Earth rotates somewhat unevenly, and because its axis is tilted at 23.4 degrees, that moment of true noon very rarely lines up with 12 o'clock on your clock. If you were to walk either east or west by just 1 degree of longitude, a distance of roughly 111 kilometers, your personal true noon would shift by approximately 4 minutes. This means that even 2 neighboring towns can and do experience the sun's highest point at slightly different times. Before the invention of mechanical clocks, people lived their lives according to this solar rhythm. Each individual town kept its own local time, based entirely on the sun's position. Noon was simply the moment when the sun stood highest overhead, and that was sufficient. But when railways and telegraphs began to connect cities in the 19th century, this localized system completely fell apart. Trains could not operate on a safe or reliable schedule if noon meant something different every few kilometers down the track. And so, in the year 1884, at the International Meridian Conference held in Washington, D.C., scientists and diplomats came to an agreement. They decided to divide the entire planet into 24 standardized time zones, with each zone covering 15 degrees of longitude. They formally established the prime meridian as the line passing through Greenwich, England. And from that single line, Standard Time was born. Time zones successfully solved the logistical chaos, but in doing so, they also quietly obscured the natural irregularities of the planet's motion. When your phone automatically switches time zones as you cross a border, it is following a human-constructed grid, not the sun's natural logic. For example, when it is exactly 12 o'clock noon in Paris, France, the sun is already past its highest point in the sky. In Beijing, China, a city which technically spans 5 theoretical time zones but officially uses only 1, noon on the clock can arrive when the sun is still visibly climbing toward the horizon. This discrepancy between solar noon and clock noon can reach as much as 2 hours, depending entirely on where you are physically located within a given time zone. In Spain, for instance, the local solar noon often occurs around 2 o'clock p.m. Standard Time. a historical remnant of political time shifts made during the 1940s. NASA's Goddard Space Flight Center explains this very simply. The sun does not follow our clocks. Our clocks follow convenience. What began merely as a practical adjustment for travel and communication became, over time, a quiet separation between human society and the actual physical motion of the Earth. But even the concept of solar noon is not fixed. Because Earth's orbit is elliptical, and because its rotational speed varies slightly throughout the year, as described by Kepler's laws, the sun's apparent position in the sky fluctuates. This variation creates the equation of time, which we explored earlier, the difference between true solar time and mean, or average, solar time. As a direct result of this, true solar noon can drift by as much as 16 minutes over the course of a single year. If you were to plot the sun's position at the exact same clock time every day for a year, the result would not be a single dot or a straight line. It would be a looping figure-8 pattern known as the analemma, which you can sometimes find printed on old terrestrial globes. That unique shape is the composite fingerprint of Earth's axial tilt and its elliptical orbit combined. It serves as a visual reminder that our planet's motion is graceful but never perfectly regular. Data from the Gaia mission and NASA's JPL Horizons system now allow scientists to model these variations down to mere fractions of a second. The exact timing of solar noon at any specific point on Earth can be predicted with accuracy for centuries in advance, simply because the laws of orbital mechanics are that consistent. And yet, despite all of this available precision, our daily lives are constructed around averages, around mean time, not real time. Every clock you own is synchronized to something called Coordinated Universal Time, or UTC. UTC is maintained by a global network of atomic clocks that measure time based on the vibrations of cesium atoms, which oscillate at 9,192,631,770 cycles per second. But the Earth itself does not keep perfect pace with that atomic standard. Its rotation is gradually slowing down, primarily due to the tidal friction exerted by the Moon, which slowly transfers angular momentum away from the Earth. To keep UTC aligned with the Earth's solar time, international agencies must occasionally insert a leap second. This is a 1-second adjustment designed to prevent our clocks from drifting too far away from the planet's real, physical motion. The most recent leap second was added in the year 2016. NASA physicists often describe this balance as a form of temporal housekeeping. It is our systematic way of keeping human-defined time and cosmic time from diverging too significantly. However, over the coming decades, as atomic time becomes ever more stable and Earth's spin continues to slow down irregularly, scientists are actively debating whether to abolish the leap second entirely. If that decision is made, our official time will begin to slowly but permanently separate from the rhythm of the sun, drifting by approximately 1 minute every 50 to 100 years. This is a small drift at first, but it is cumulative. Eventually, 12 o'clock noon on the clock could arrive while the sun is still rising. In many respects, that shift has already commenced. The proliferation of artificial light has effectively untethered us from the solar cycles. GPS satellites and atomic clocks now measure time at a resolution far beyond human perception. Time zones, which are political, not physical, boundaries, now define how we live, work, and sleep. But beneath all of that human-imposed structure, the natural world continues its own rhythm, quietly, precisely, and predictably. The real sun still crosses every single meridian once per day, whether or not anyone bothers to look up and see it happen. Neil deGrasse Tyson once remarked, We are part of this universe. We are in this universe. But perhaps more important than both of those facts is that the universe is in us. That holds true for time as well. Every second we measure is, in reality, borrowed from the movement of the cosmos itself. When the sun reaches its highest point in the sky tomorrow, it may not be at exactly 12 o'clock. It may occur a few minutes before or a few minutes after, depending entirely on your longitude, the specific date, and the immutable laws of orbital geometry. But that quiet difference, that beautiful imperfection, is a fundamental truth of astronomy. No two places on Earth ever share the exact same noon. The next time you see your clock strike 12, remember, it is not the universe that has changed to match your time. It is you who has adjusted the universe to fit your schedule. And as we follow that adjustment even deeper, something else quietly reveals itself. The more precisely we learn to measure time, the more we come to realize that the Earth is not just spinning, it is drifting, carried along on a vast invisible current of motion. Which leads us to a much larger and final question. Part 5. Where is the Earth really going right now? As you sit or lie still, you are simultaneously moving through the galaxy at a speed approaching 792,000 kilometers per hour. You do not feel this motion because everything in your immediate environment is moving along with you. But make no mistake, the ground beneath your feet, the air above your head, and even the sun in the sky, all of it is racing through the depths of space. The question is, where are we all going? Most people are aware that the Earth spins on its axis once every 23 hours and 56 minutes. It is also common knowledge that it orbits the Sun once every 365.25 days, traveling at about 108,000 kilometers per hour. But these are only the first two layers of our motion. Beyond them lies a deeper, faster drift, one that carries not just the Earth, but our entire solar system on a massive journey through the Milky Way galaxy. Our Sun, along with its complete family of planets, moons, and asteroids, is in orbit around the galactic center. This is a region located approximately 26,000 light-years away from us, situated in the direction of the constellation Sagittarius. Astronomers have confirmed that this center conceals a supermassive black hole, known officially as Sagittarius A star, which possesses a mass roughly 4 million times greater than that of our Sun. Even at this enormous distance, gravity still reigns supreme. The Sun is pulled along an orbital path that is roughly circular, completing one full revolution around the Milky Way every 230 million years. This journey is often referred to as one galactic year. During that immense span of time, the Earth and everything upon it travels approximately 9 trillion kilometers. NASA's Goddard Space Flight Center describes it concisely. Our entire solar system orbits the center of the Milky Way galaxy at a speed of about 220 kilometers per second. That velocity translates to over 792,000 kilometers per hour. And yet, the stars that surround us in the night sky appear almost stationary because they too share in that colossal motion. But the Milky Way galaxy itself is not at rest. The European Space Agency's Gaia mission, which is meticulously tracking the positions and velocities of over 1.5 billion stars, has revealed that our galaxy is currently moving toward a mysterious, dense region of the cosmos known as the Great Attractor. This region is located between the constellations of Leo and Virgo. The Milky Way and all of its neighboring galaxies, including Andromeda, Triangulum, and thousands of others, are being inexorably drawn toward this gravitational anomaly at a staggering speed of about 2.1 million kilometers per hour. What is the Great Attractor? It is not a single object like a black hole or a massive star cluster. Instead, it appears to be a gravitational focal point situated within an unimaginably massive region of space called the Laniakea supercluster. This structure contains more than 100,000 galaxies, all spread across a distance of 520 million light-years. According to data from the Center for Astrophysics at Harvard and Smithsonian, the Great Attractor simply marks the direction in which our entire cosmic neighborhood is flowing. It is a vast gravitational valley that bends the trajectories of countless galaxies, much like rivers following the inevitable pull of the terrain. And yet, even this immense structure is not stationary. Beyond it, there is evidence of another, even larger gravitational drift, pulling us toward the Shapley supercluster, which is even farther away. This suggests that the universe's large-scale structure is in a state of constant dynamic motion. This means that every single point in the universe, from the smallest particle of dust to the largest supercluster of galaxies, is moving relative to something else. There is no fixed center to the cosmos. There is no universal up or down. As NASA astrophysicist Michelle Thaler has explained, there is no place of rest in the cosmos. Everything is orbiting something else. To put this in perspective, while you sleep for 8 hours tonight, the Earth will have rotated once on its axis relative to the stars by about 120 degrees. It will have traveled 864,000 kilometers along its orbit around the Sun, and it will have been carried 6.3 million kilometers on its journey through the Milky Way galaxy. Yet, our human senses detect none of it. Why? It is because all of these motions are shared. The air, the oceans, and your own body all move together as one single inertial system. Within that shared frame of reference, you feel perfectly still, even as the entire planet streaks through the darkness at an unimaginable speed. This is one of the most remarkable features of physics. Motion is relative. Without an external reference point, you cannot detect constant velocity. You can only measure acceleration, that is, a change in speed or a change in direction. Since Earth's orbital and galactic motions are, for the most part, nearly uniform, they feel completely silent, perfectly steady, and totally invisible. Data from the Gaia mission has also revealed that the Sun's path through the Milky Way is not flat. It actually oscillates up and down through the galactic plane in a gentle wave, rising approximately 70 light-years above and below the disk, and completing one full vertical cycle every 64 million years. Some scientists have even speculated that these oscillations might influence the rate of comet impacts on Earth, as the solar system periodically passes through denser regions of interstellar material. The idea of layered motion continues even farther out. The Milky Way itself is a member of the Local Group, which is a small, gravitationally bound collection of galaxies, including our large neighbor, Andromeda, M31, and the smaller Triangulum galaxy, M33. These galaxies are intrinsically linked by the fundamental force of gravity and are relentlessly, slowly drawing closer together. In a span of approximately 4 billion years, our own Milky Way galaxy and the neighboring Andromeda galaxy are destined to collide and merge, ultimately forming a single, massive elliptical galaxy. This incredible cosmic event is not merely a distant forecast. It is an occurrence already observable in its progression, thanks to precise measurements gathered by the Gaia spacecraft. Gaia has clocked Andromeda's approach speed at roughly 110 kilometers per second. Beyond this immediate galactic neighborhood, our local group of galaxies is, itself, a constituent part of the far vaster Laniakea supercluster. Furthermore, this entire immense cosmic region is moving with respect to the cosmic microwave background, often abbreviated as the CMB, which is the faint, residual thermal radiation, or afterglow, left over from the Big Bang. Our collective velocity relative to this primordial light is estimated to be about 630 kilometers per second. Scientists are able to measure this grand motion by observing what is known as the CMB dipole. This dipole represents a subtle, yet measurable difference in temperature across the expanse of the sky, an anomaly directly caused by our movement relative to the universe's most ancient light. In simpler terms, the lingering echo of creation itself serves as confirmation that we are never truly still. Every single second, we drift deeper into uncharted territories of space-time, never to occupy the same cosmic coordinates again. When you gaze up at the night sky, you are, in fact, looking into the past, but you are also simultaneously moving through that past. The stars you observe tonight are not in the identical positions they held even a mere few thousand years ago. Some of them have already ceased to exist, their light still traversing the vast emptiness of space on its long journey toward us. Carl Sagan famously remarked, "We are like butterflies who flutter for a day and think it is forever." When measured against the scale of cosmic motion, that analogy is precisely what we are. We are transient passengers occupying a moving world, which is itself part of a moving system, which is inside a moving galaxy, all drifting through a universe that is, itself, expanding. This profound understanding does not originate from mere imagination. It is built upon hard data. It comes from data gleaned from Doppler shifts measured by powerful radio telescopes, from meticulous proper motion charts compiled by the European Space Agency's Gaia mission, and from detailed microwave observations gathered by NASA's WMAP and Planck missions. Collectively, these sophisticated projects map our velocity through the cosmos with astonishing precision. The Planck satellite, for example, confirmed that our galaxy is moving at approximately 370 kilometers per second relative to the cosmic microwave background. This is tangible proof that the Milky Way itself is an active participant in a grand, overarching cosmic flow. Therefore, if we were to pose the question, where is Earth going? The scientific answer is simultaneously everywhere and nowhere fixed. We are traveling in orbits nested within other orbits, a complex series of nested loops of motion, all governed by the force of gravity. Each of these loops is merely one part of a much larger system. From the tiniest rotations of electrons to the massive spinning of stars, movement defines existence itself. It is not the exception to the rule, it is the rule. And although we have successfully mapped a great deal of this motion, our ultimate, full destination remains unknown. The Great Attractor, despite its immense gravitational influence on our region of space, is partially obscured from our view. It lies hidden behind what astronomers call the zone of avoidance, a region of the sky blocked by the dense dust and gas clouds of our own Milky Way galaxy. The James Webb Space Telescope, or JWST, is now actively observing the universe in deeper infrared wavelengths. These wavelengths possess the ability to penetrate that obstructive dust, helping scientists to finally reveal what truly lies at the core of this significant gravitational anomaly. Early data from these observations suggest the presence of massive galaxy clusters and immense concentrations of dark matter, all conspiring to shape the gravitational field in that area. It is perhaps one of the largest known structures in the nearby universe. Every new image captured adds weight to the same fundamental truth. Space itself is in motion. The cosmic web, those vast filaments of galaxies stretching across billions of light years, sways, collapses, and expands, carrying us along with it. From the room you are in right now to the most distant quasars, every single point in the universe is temporary. Every position is just one segment of a much larger orbit. If you could somehow freeze time at this very instant, mark your exact coordinates in space, and then check those coordinates again just 1 second later, you would find that you are already billions of meters away from that spot, relative to the galaxy's frame of reference. The ground beneath our feet feels solid only because we are all moving together in unison. And that, perhaps, is the quiet wonder of astronomy. It teaches us that motion is not something that is happening to us. It is something we are fundamentally a part of. Tomorrow, when you stand under the light of the sun, try to visualize the invisible arcs you are tracing through space. The Earth spinning on its axis, orbiting the sun, and spiraling through the Milky Way. All of it, all of us, being pulled inexorably toward a distant, unseen point. And if everything we know is perpetually in motion, then what does it truly signify to count a single day? Part 6. A day isn't really 24 hours. Every clock on Earth is lying to you, but only by a very small amount. We have been told throughout our lives that a day lasts for exactly 24 hours, and yet, in the precise language of astronomy, that is not quite true. The Earth does not actually require 24 hours to spin once on its axis. It only needs 23 hours, 56 minutes, and 4 seconds. This specific period is known as the sidereal day. So, where did those missing 4 minutes go? The answer to that question reveals one of the most subtle and beautiful truths about how our planet moves through space. A sidereal day measures one complete rotation of the Earth relative to the distant stars, the fixed, unchanging background of the cosmos. It is the purest measure of rotation available, and it is the standard used by astronomers to track the true spin of the planet. But while the Earth is busy spinning, it is also simultaneously orbiting the Sun. During that single 23-hour, 56-minute, and 4-second rotation, the planet moves approximately 2.5 million kilometers along its orbital path. By the time it completes one full 360-degree turn relative to the stars, the Sun is no longer in the same position in the sky that it was. To bring the same longitude on Earth back into alignment with the Sun, our planet must rotate about 1 degree more. This extra rotation takes roughly 4 extra minutes. That is precisely why the solar day, the interval we measure from one noon to the next, is 24 hours long. The sidereal day is shorter because its frame of reference, the distant stars, isn't moving, whereas the Sun appears to shift its position as the Earth travels along its orbit. This small discrepancy might seem trivial, but it represents one of the key differences between how human beings experience time and how astronomers measure cosmic motion. NASA's Goddard Space Flight Center explains it this way. A sidereal day measures Earth's rotation relative to the stars, while a solar day measures it relative to the Sun. The difference is about 4 minutes. That 4-minute drift accumulates rapidly. After 1 month, the stars will appear to rise approximately 2 hours earlier than they did at the beginning of the month. After 1 full year, the difference completes a full 24-hour cycle, which is the exact reason why the constellations visible in the night sky change with the passing seasons. In July, for instance, the constellation Scorpius dominates the southern sky. 6 months later, in January, it has been replaced by the constellation Orion. This cyclical change is one of the most fundamental and prized rhythms in the field of observational astronomy. Telescopes, especially those mounted on equatorial tracking systems, rely heavily on sidereal time to follow celestial targets accurately. Unlike solar time, which drifts along with the sun's apparent position, sidereal time remains firmly tied to the fixed stars. When astronomers at the European Southern Observatory, ESO, aim their powerful telescopes at a distant star, they synchronize their systems not to the 24-hour clock of human life, but to the 23-hour, 56-minute clock of the universe. This synchronization ensures the telescope moves in perfect sync with the Earth's rotation relative to the stars, keeping the target object centered in the field of view. Even space-based observatories, like the Hubble Space Telescope and the James Webb Space Telescope, JWST, operate using sidereal principles. Their sophisticated pointing systems use catalogs of reference stars, mapped with sub-arc-second precision, to maintain perfect alignment. A deviation of even 1 second of time corresponds to a drift of about 15 arcseconds in the sky, more than enough to blur the sharpest images of distant galaxies. So, while you measure your day using a wall clock, astronomers measure their day by the stars. This difference also implies that time itself possesses layers, one layer for human activity, and another for the mechanics of the cosmos. If you were to decide to live your life entirely by sidereal time, your day would shift 4 minutes earlier every single day. After 6 months, your personal midnight would occur at what solar time observers would call noon. After a full year, you would loop back into alignment once again. The Earth's spin rate is not perfectly constant either. Geological processes, the gravitational pull of ocean tides, and even the redistribution of mass resulting from melting glaciers can slightly alter the length of the day. According to NASA's Jet Propulsion Laboratory, the average length of a day increases by about 1.7 milliseconds per century. This is mostly due to tidal friction, the gravitational tug of the Moon, which is slowly but steadily slowing the Earth's rotation. This means that hundreds of millions of years ago, days were significantly shorter. They were only about 22 hours long during the age of the dinosaurs. Scientists have confirmed this by studying natural calendars, such as ancient coral growth rings and tidal sediment layers. These records show that the ancient Earth experienced about 400 days per year, instead of the 365 we have now. Each day was shorter, but the total time it took to orbit the Sun remained the same. This gradual deceleration continues today. It is imperceptibly small on a human timescale, but it is measurable with highly precise atomic clocks. To keep our modern timekeeping systems in sync with the Earth's slowing spin, international time standards occasionally require the addition of a leap second to Coordinated Universal Time, UTC. Without these tiny adjustments, the difference between solar time, based on rotation, and atomic time, based on physics, would grow into minutes over the span of centuries. The International Earth Rotation and Reference System Service, IERS, monitors these variations using data from techniques like Very Long Baseline Interferometry, VLBI, and satellite laser ranging. These tools can measure the planet's rotational phase to within microseconds, allowing scientists to detect even the most minuscule wobbles in the Earth's spin. But why does all this precision matter? It matters because understanding sidereal time is crucial for everything from tracking satellites in orbit to navigating spacecraft across the solar system. When NASA sends probes to Mars or beyond, mission planners must calculate their launch windows based on the precise rotational position of Earth relative to the target planet. A 4-minute miscalculation in sidereal alignment could potentially shift a spacecraft's trajectory by thousands of kilometers. That is why mission control rooms often display both UTC and local sidereal time, LST, side by side. Astronomical events, such as occultations, eclipses, or planetary transits, are all predicted using sidereal models, not solar ones. If you have ever noticed that the stars seem to rise just a little bit earlier each night, you are observing the sidereal clock, quietly ticking away beneath our human-centric schedule. It is the true heartbeat of the Earth's rotation, the one that nature follows, even if our watches choose to ignore it. As Carl Sagan once said, we are a way for the cosmos to know itself. To truly know the cosmos, we must first understand the true rhythm of our own world. This means not the 24-hour rhythm we constructed for our convenience, but the precise rotation that is written into the fundamental geometry of the universe. This sidereal day, this 23 hours, 56 minutes, and 4 seconds, defines how our planet relates to everything beyond it. It dictates how the night sky shifts, how telescopes must aim, and how cosmic coordinates can remain stable across decades of observation. Without it, the science of astronomy would lose its anchor. Yet, the difference between a solar and a sidereal day also tells a larger story about the constant interplay between motion and time. The extra 4 minutes that we experience each day accumulate because we are never still, not even for a single moment. The Earth's orbit around the Sun adds that small delay to every rotation, serving as a constant reminder that our spinning world is also on a grand journey around its star. ESA scientists sometimes refer to this phenomenon as compound motion, two simultaneous rotations combining into a single, elegant cycle that defines our experience of time. It is not an error in the system. It is the natural signature of a planet in motion. If you stand outside at midnight and look due south, the stars you see crossing the meridian tonight will cross that same line 4 minutes earlier tomorrow night. That steady, predictable drift is the reason constellations change with the seasons. Orion rising in winter, Scorpius rising in summer. The sidereal clock quietly advances, carrying our view of the universe forward, night by night. So, the next time you see a clock strike midnight, remember that it is midnight only according to Earth's solar schedule. The universe, in its own time, has already moved on. Somewhere above you, the sidereal day has already finished its turn. Precise, unbroken, and far older than human timekeeping itself. And that is the hidden truth behind our most familiar measure of time. A day isn't truly 24 hours. It is 23 hours, 56 minutes, and 4 seconds, plus the motion of a planet that never stops moving around its star. But what if that spin, just slightly tilted, is the very reason we have seasons, storms, and life itself? Part 7. Tilted by 23.4 degrees. This is the small angle that controls Earth's climate. If the Earth were not tilted, if its axis stood perfectly straight up and down like a flawlessly balanced top, there would be no summer, no winter, and no seasons at all. The world would be locked in a permanent, monotonous twilight. The equator would be perpetually hot, the poles would be perpetually frozen, and every sunrise would be exactly like the one before it. But because our planet leans just 23.4 degrees from the vertical, everything changes. This small tilt, known technically as the axial tilt or obliquity, is the fundamental reason the Earth breathes in seasons. It is what decides when crops grow, when ocean currents shift, when monsoons arrive, and when the polar ice caps expand or retreat. In the grand scheme of astronomy, 23.4 degrees might sound trivial. Yet, it is undeniably one of the most influential numbers in the entire history of life on this planet. The concept itself is simple. The Earth's axis of rotation is not perpendicular to the plane of its orbit around the Sun. As the planet travels along its elliptical path, the northern and southern hemispheres take turns leaning toward the Sun. When the North Pole tilts sunward, sunlight strikes the northern hemisphere more directly. The same amount of solar energy is concentrated onto a smaller surface area, which produces higher temperatures. This is summer. 6 months later, the tilt is reversed relative to the Sun. The southern hemisphere faces the Sun, experiencing its summer, and the north cools into winter. NASA's Earth Observatory explains this with perfect clarity. Seasons are caused not by the Earth's changing distance from the Sun, but by the tilt of its rotational axis. In fact, at perihelion, the point when Earth is closest to the Sun, around early January, the northern hemisphere is actually experiencing winter because it is tilted away from the Sun's direct rays. The changing distance only slightly affects temperature. It is the angle of the sunlight that does the rest of the work. This simple geometry shapes everything we know about climate. At the equator, sunlight arrives at a nearly perpendicular angle all year round, which keeps the conditions consistently warm. At higher latitudes, the sun's rays arrive at much shallower angles. This spreads the same amount of energy across wider surfaces, resulting in cooler climates. The tilt also explains why the Arctic Circle, located at 66.5 degrees north latitude, experiences days without night in the summer and nights without day in the winter. For weeks on end, the sun either never sets or never rises, depending on the season. This is a direct consequence of that 23.4-degree tilt. Data from the Gaia mission has refined our understanding of this motion. The Earth's axial tilt is not fixed. It actually wobbles slowly, a phenomenon known as axial precession, completing one full cycle roughly every 26,000 years. This gradual change alters the timing of the seasons relative to Earth's orbit, which in turn subtly shifts long-term climate patterns. Furthermore, over tens of thousands of years, this tilt oscillates between 22.1 degrees and 24.5 degrees. This oscillation is driven by the gravitational influences of the Moon and other planets. These variations are part of what scientists refer to as the Milankovitch cycles, named after the Serbian astrophysicist Milutin Milankovitch. It was Milankovitch who, in the 1920s, demonstrated how these subtle changes in Earth's orbit and tilt caused the periodic advance and retreat of the great ice ages. According to NASA's Goddard Institute for Space Studies, JWST, when the tilt angle increases, seasons become more extreme, warmer summers and colder winters. When the tilt angle decreases, the seasons mellow out, allowing ice sheets to expand. The current tilt of 23.4 degrees lies near the middle of its operational range, giving Earth a stable climate that is ideal for the development of complex life. Without that stabilizing tilt, our planet would be a far more hostile place. Scientific models show that a perfectly upright Earth, one with no tilt, would have minimal seasonal change. This would leave the poles locked in frigid darkness year-round and would severely reduce atmospheric circulation. Weather patterns would flatten, the jet stream would likely collapse, and rainfall would lose its predictable seasonal cycles. Agriculture, which is entirely dependent on seasonal variation, would never have evolved. Even more remarkable is how the tilt manages to stay so steady. Our moon plays a crucial role in this. The moon's gravitational pull acts as a stabilizing anchor, preventing Earth's tilt from swinging wildly. Without the Moon, computer simulations demonstrate that the Earth's axial tilt could vary chaotically, oscillating anywhere between 0 degrees and 85 degrees. This would produce catastrophic climate swings every few million years. As NASA scientists have stated, the Moon may very well be the reason Earth's climate has remained stable enough for complex life to develop and thrive. At the poles, the consequences of the tilt are dramatic. During the summer solstice in the northern hemisphere, around June 21st, the North Pole points directly toward the Sun, and the Sun does not set for several weeks. At that exact same time, the South Pole is facing away, plunged into total darkness. 6 months later, the roles are precisely reversed. The exact moment of the solstice marks when the Sun's apparent path across the sky reaches its northernmost or southernmost point. These are the boundaries of our annual sunlight cycle. The equinoxes, which occur around March 21st and September 23rd, are the balancing points in the orbit. On these days, sunlight reaches both hemispheres equally, and day and night last for approximately 12 hours each, everywhere on Earth. This delicate choreography of angles is what defines Earth's climate zones. It dictates where deserts form, how the winds blow, and where life is able to thrive. When the tilt changes, even slightly, so do the boundaries of entire ecosystems. The National Oceanic and Atmospheric Administration, NOAA, uses this understanding to model the flow of global energy. They calculate that during the Northern Hemisphere's summer, the top of the atmosphere receives about 480 watts per square meter of solar power at the pole. This is compared to less than 100 watts per square meter in the winter. That massive difference in energy input is what drives ocean currents, atmospheric circulation, and even the large-scale migration of animals. The James Webb Space Telescope, JWST, is now studying exoplanets with measurable axial tilts, searching for other worlds that might share this stabilizing geometry. Astronomers have already found planets with extreme axial tilts, some tilted more than 80 degrees, effectively flipping their poles directly toward their stars. Those worlds would experience bizarre seasons lasting for years or even decades. Other planets have been found spinning perfectly upright, with almost no seasonal change at all. Neither of these extremes seems favorable for life as we know it. That makes Earth's 23.4-degree angle unusually gentle, a perfect compromise between climatic variety and long-term stability. Carl Sagan once wrote, "Our planet is a lonely speck in the great enveloping cosmic dark." And yet, that tiny lean, that slight imperfection in its spin, is what makes this speck alive. Even within this balance, there are measurable drifts. Data from NASA's Jet Propulsion Laboratory show that the Earth's tilt changes by about 2.4 arcseconds per year. This is a minuscule motion. But over thousands of years, it completely reshapes the distribution of sunlight across the latitudes. This slow modulation of solar input has been definitively linked to the onset of glacial and interglacial periods, the very heartbeat of Earth's long-term climate history. As you listen to this, the Earth continues to tilt, not changing its angle suddenly, but maintaining its orientation in space as it orbits the Sun. This constancy means that throughout the year, the planet presents different faces to the Sun. That simple geometry is what allows you to stand under a warm summer sky one month and see snow falling the next. Climate models confirm that if the tilt were even slightly greater or smaller, the distribution of energy would shift enough to transform entire ecosystems. The polar ice caps would either melt dramatically or expand far down into the continents. A change of just 2 degrees could rearrange weather patterns worldwide. every calendar, every crop, and every migration on Earth traces its origins back to that 23.4 degrees. The line of direct sunlight drifting north and south across the equator, known as the solar declination, is what defines our seasons, our harvests, and the very rhythm of our daily lives. It is extraordinary that a single number, 23.4, can hold such immense power. It is the quiet architecture behind every breeze, every rainfall, and every leaf that turns color and falls. If you could step back far enough from our planet and watch the Earth orbiting the Sun, you would see it as a spinning sphere, leaning gently on its side, tracing an invisible circle in space. That lean, slight, but constant is what paints the planet's surface with the patterns of light and shadow that shift through the year. As Neil deGrasse Tyson put it, we are participants in a grand cosmic dance, one choreographed by the forces of nature. Tomorrow, when sunlight warms your face, remember that it reaches you not because the sun changed, but because the Earth leaned just right. And that lean, that 23.4-degree tilt, may be one of the rarest and most precious coincidences in the entire universe. Yet, the story of Earth's motion doesn't end there. Because while the tilt sculpts our seasons, time itself must be constantly adjusted, trying to keep pace with a planet that never turns exactly the same way twice. And that is where our next quiet journey leads, into the strange arithmetic of leap years and the delicate corrections that keep our calendars aligned with the drifting sky. Part 8. Leap years are not mistakes, they are corrections. Every 4 years, we add a single day to the calendar, and almost no one stops to ask why. It seems like a small, arbitrary quirk of the calendar, a rare February 29th that slips quietly into the year. But that extra day is not an error. It is a precision adjustment, a subtle but necessary correction that keeps human time tethered to the true motion of the Earth. The planet does not take exactly 365 days to complete one orbit of the Sun. It actually takes 365.24219 days. This amounts to about 365 days, 5 hours, 48 minutes, and 45 seconds. This small fraction, just under a quarter of a day, means that every year our calendar drifts slightly ahead of the real seasons. After 4 years, that drift accumulates to nearly one full day. That is why every 4th year, we insert February 29th. We do this not as a matter of convenience, but as a mathematical necessity. Without it, our seasons would slowly slide out of alignment. Within just a few centuries, spring would begin in what our calendar calls February, and eventually, winter would arrive in July. NASA's Goddard Space Flight Center explains it simply. Leap years keep our calendar aligned with Earth's revolutions around the Sun. Without them, the calendar would fall completely out of sync with the seasons. The idea of adding extra days is not new. Ancient astronomers noticed long ago that the solar year did not fit neatly into whole numbers. The Egyptians were among the first to adopt a 365-day calendar, but over time, they realized their New Year's Day was drifting relative to the annual, life-giving flooding of the Nile. The Romans faced the exact same problem. In 46 BCE, Julius Caesar ordered a comprehensive reform, creating what became known as the Julian calendar. The Julian system assumed the year lasted 365.25 days, and it simply added one leap day every 4 years. This worked well at first, but it slightly overcompensated. That tiny error, the extra 0.00781 days per year, which amounts to about 11 minutes, began to add up. After 128 years, the Julian calendar was ahead of the real sun by about one full day. By the 16th century, the difference between the calendar and the seasons had grown to nearly 10 days. The spring equinox, which was supposed to occur around March 21st, was actually happening on March 11th. To fix this accumulating error, Pope Gregory XIII commissioned a new system in the year 1582, guided by the expert advice of the astronomer Christopher Clavius. The Gregorian calendar made one small but elegant change. Century years, like 1700, 1800, and 1900, would not be leap years unless they were divisible by 400. This subtle rule brought the average length of the calendar year to 365.2425 days, which is nearly identical to the true tropical year. This reform required an immediate and jarring correction. To realign the calendar with the equinox, 10 days had to be dropped. Thus, in the year 1582, Thursday, October 4th, was immediately followed by Friday, October 15th. The world literally skipped 10 days just to repair the flow of time. At first, not everyone accepted this change. Protestant countries, inherently suspicious of a papal decree, resisted and clung to the old Julian system for centuries. Britain and its colonies, for example, did not adopt the Gregorian system until the year 1752. By that point, the discrepancy had grown to 11 days. Citizens were confused and, in some cases, angry. Some people genuinely believed the government had stolen part of their lives. But it was not theft, it was synchronization. The Earth had kept moving, and humanity was simply catching up. ESA historians often call the Gregorian reform the most successful correction in human history. It unified global timekeeping and finally brought the civil calendar into harmony with astronomical reality. Today, almost every nation on Earth uses this system, with only a few exceptions that maintain traditional calendars for cultural or religious reasons. The precision of leap years matters more today than ever before. NASA's Jet Propulsion Laboratory, JPL, relies on this exact system to plan spacecraft trajectories, planetary encounters, and complex orbital models. Even a drift of a few minutes per year could throw off the timing of interplanetary missions by thousands of kilometers. Astronomers and engineers often measure time in Julian dates, a continuous count of days that have passed since January 1st, 4713 BCE, specifically to avoid the discontinuities of calendars altogether. But for civil life, the Gregorian calendar remains the gold standard. Its design ensures that the average year deviates from the true tropical year by only 26 seconds. That is an error of just 1 day every 3,300 years. Still, even this remarkable accuracy is not perfect. As we've learned, the Earth's rotation is slowly decelerating due to tidal friction with the Moon. The length of a day increases by about 1.7 milliseconds per century. Over millennia, this tiny effect will require further corrections. Future scientists may eventually need to redefine what we mean by a day or a year. But for now, leap years keep us remarkably close to the true rhythm of the cosmos. The International Earth Rotation and Reference System Service, IERS, monitors this delicate balance, ensuring that atomic time, which is defined by the oscillations of cesium atoms, remains synchronized with astronomical time. Occasionally, the IERS introduces a leap second, just as we add leap days, to ensure our atomic clocks perfectly match the planet's actual spin. So, in reality, both our seconds and our days are under constant, careful adjustment. The result is a world where our sense of time, from our daily schedules to our most ambitious space missions, is anchored by mathematical corrections hidden just beneath the surface of every calendar. Neil deGrasse Tyson once remarked, "We don't measure time by the clock. We measure it by change. That is exactly what leap years do. They measure change. They account for the change in Earth's orbit, the slow drift of its rotation, and the difference between human-made order and true cosmic motion. It is humbling to realize that even our most universal system, the calendar, is not fixed. It is a living construct, one that is continually refined to keep pace with an imperfectly moving planet. Without these small, intelligent interventions, history itself would lose its alignment with the world it attempts to describe. Think of this. Every leap day is humanity's way of resetting its clock to match the universe. Every February 29th, we quietly reattach ourselves to the orbit that defines us. The world turns, the sun returns to its proper place, and time, for a moment, feels exact again. This precision extends far beyond daily life. The James Webb Space Telescope, JWST, operates on strict orbital mechanics that are tied to both solar and sidereal timing. Engineers plan its observations months in advance using complex algorithms that incorporate the leap year cycle. Missing a single correction could shift a scheduled observation window by hours, thereby altering the telescope's alignment with its distant targets. So that single day, February 29th, matters across all disciplines, from the simple keeping of birthdays to the complex tracking of distant galaxies. It is a testament to the human desire to stay synchronized with the cosmos. When you look at your calendar and see that rare extra day, remember that it represents 5 hours, 48 minutes, and 45 seconds of accumulated drift. It is the exact difference between the time we live by and the time the Earth truly keeps. It is one of the most elegant examples of science woven invisibly into our daily lives. Every 4 years, we remind ourselves that precision is not about achieving perfection. It is about mastering adjustment. Carl Sagan once said, "Science is not only compatible with spirituality, it is a profound source of spirituality." The leap year embodies that spirit. It is a union of logic and wonder, where mathematics quietly preserves our essential link to the stars. Our timekeeping, then, is not static. It is a partnership between the motion of the Earth and the minds that have learned to measure it. Each correction, each adjustment, keeps us aligned with the geometry of our orbit, with the quiet, imperfect rhythm that defines a year. But what about the journey we make within that rhythm? The incredible distance each of us travels, carried through space by the turning world beneath our feet. Part 9. The physical journey of a human lifetime. You have never been still. Not for a single second of your life. Even as you sleep, you are traveling through the cosmos at a speed faster than any spacecraft humanity has ever managed to build. In the span of an average lifetime, say 100 years, you will have drifted with the Earth for more than 900 billion kilometers through space. That journey begins the moment you are born. The hospital room where you take your first breath is already spinning at about 1,670 kilometers per hour as the planet rotates on its axis. At that very same time, you are orbiting the Sun at 108,000 kilometers per hour. You are also moving around the galactic center at nearly 792,000 kilometers per hour. And the entire Milky Way galaxy is gliding toward the Great Attractor at over 2.1 million kilometers per hour. Every single moment of your existence is spent in motion. You are living within an unbroken chain of trajectories, stacked one inside the other. NASA describes this beautifully. Our entire solar system is moving through the galaxy at roughly 220 kilometers per second, carrying everything within it along for the ride. So even when you sit quietly, or when you lie down to rest, You are crossing millions of kilometers every single day. Each night's sleep, perhaps 8 hours of silence, equates to roughly 3 million kilometers of travel through the galaxy. Yet you feel nothing. Not a vibration, not a sway, not even a whisper of acceleration. Why is that? It is because all of it, the air, the oceans, the planet's crust, the atmosphere, moves with you as one single, cohesive unit. The sensation of stillness is an illusion, one created by shared motion. From the perspective of physics, you are part of an inertial frame of reference. This is a moving system where everything inside it shares the exact same velocity. Unless that motion changes, unless there is acceleration or resistance, it becomes invisible. It is the very same principle that allows astronauts to float weightlessly aboard the International Space Station, ISS. They are not escaping gravity. They are falling around the Earth in a state of perpetual freefall. They are traveling at 27,600 kilometers per hour along a curved path that perfectly matches the planet's shape. The result is a serene, unbroken glide, motion without the feeling of movement. You are experiencing a gentler version of that exact same phenomenon every moment of your life. The European Space Agency's Gaia spacecraft, which is meticulously mapping the positions and motions of more than 1.5 billion stars, has shown that our Sun traces a slightly wavy orbit through the Milky Way. It follows a spiral path that oscillates above and below the galactic plane about every 32 million years. As you go about your daily life, eating, breathing, sleeping, your body follows that exact same oscillation, carried through the thick, star-filled arms of the galaxy. If someone could look down from a vantage point far above our galaxy, they would see the solar system moving like a glowing ribbon. They would see the planets orbiting the sun itself drifting through the galaxy, and the galaxy itself being drawn toward unseen structures in the distant universe. Every human being, every cloud, every single grain of sand is part of that incomprehensible motion. Neil deGrasse Tyson once said, "We are not just in the universe is in us." That is literally true. The atoms that make up your body, which were forged in the cores of ancient stars long ago, are now retracing the paths of their creators through the galaxy. Let's break down that motion. In just one day, the Earth rotates once, taking you on a 40,000-kilometer journey around its circumference, if you are at the equator. It moves about 2.6 million kilometers along its orbit around the Sun. The solar system in that same day advances another 19 million kilometers through the Milky Way. Multiply that by 365, and your yearly motion becomes staggering. It is over 7 billion kilometers per year. Over a century, that amounts to nearly 900 billion kilometers of total travel. And still, you never feel it because motion, in itself, is relative. Einstein's principle of relativity states that no experiment performed inside a closed system can reveal its own uniform motion. That is why you can pour water into a glass or light a candle indoors, even though the entire planet is flying through space at such an enormous speed. In a way, every building, every airplane, and every human body is like a sealed cabin aboard an immense, invisible ship, the Earth, gliding silently through the cosmic sea. But this motion is not perfectly smooth. The Earth wobbles slightly as it spins, its axis precessing like a slow spinning top. It also bobs slightly along its orbit due to the gravitational influence of the Moon and the other planets. These tiny perturbations, measured with incredible accuracy by NASA's Jet Propulsion Laboratory, cause shifts in Earth's orientation of just milli-arc seconds. but they are significant enough that space agencies must correct for them to achieve centimeter-level precision in spacecraft navigation. So, while you cannot feel your motion, our technology can measure it with breathtaking accuracy. The atomic clocks aboard the satellites that make up the Global Positioning System, GPS, actually tick at a slightly different rate from those on the ground. This is because of time dilation, an effect predicted by Einstein, which is caused by both their high velocity and their position in a weaker gravitational field. Without Einstein's corrections, GPS positions would drift by 10 kilometers every single day. Every modern map, every airplane route, and every ship at sea depends on understanding this intricate dance of motion and time. Our sense of being stationary is not just an illusion, it is a delicate balance of forces that allows life to exist. If the Earth were to suddenly stop spinning, the atmosphere and the oceans would continue moving at 1,670 kilometers per hour, scouring the continents clean. The calm we live in is possible only because the motion is shared, because everything moves together in equilibrium. This is what physicists call co-moving motion. It is the same reason that distant galaxies expand away from each other together as space itself stretches. On cosmic scales, the universe is not filled with stationary islands. It is a vast network of systems all moving in harmony, each carrying its contents along with it, without friction. And so, as you age, you are not only moving through time, you are being physically carried through the structure of space itself. Your entire lifetime is a physical voyage, one traced through coordinates that will never, ever be repeated. The spot in space where you took your first step, your first breath, or your first look at the night sky, all of those spots are now billions of kilometers behind you. Every moment of your memory exists in a different physical place in the galaxy. Astronomers sometimes use galactic coordinates to track positions within the Milky Way. According to data from the European Space Agency, our solar system moves about 7.3 kilometers per second toward a point near the constellation Hercules. That means that by the time tonight is over, while you sleep, you will have shifted approximately 630,000 kilometers closer to that direction, without any awareness of it at all. If you could leave a glowing trail behind you as you moved, it would form an intricate spiral, wrapping around the sun, threading through space like a bright thread woven into the fabric of the Milky Way. The James Webb Space Telescope, JWST, which orbits 1.5 million kilometers from Earth, drifts with us in that very same current. It looks backward in time, capturing light that has traveled for billions of years, even as it rides forward through the galaxy alongside the planet that built it. Everything we make and everything we observe shares that same unending motion. And yet, because our senses evolved within this shared velocity, we interpret it as stillness. It is the ultimate illusion of stability in a universe defined by perpetual travel. Carl Sagan described this perfectly. We are passengers on a little blue dot, drifting in the vast cosmic dark. That dot doesn't just float, it flies. Its motion defines our nights and days, our years and seasons, and even our sense of time itself. The next time you close your eyes to rest, think about this. In the span of your 8 hours of sleep, you will have moved nearly the distance between the Earth and the Moon, all without taking a single step. And when you wake, you will be somewhere new, on a planet that has spun, orbited, and drifted millions of kilometers farther through the galaxy. So yes, the feeling of stillness is an illusion. But it is a beautiful one. It is a quiet, elegant design of physics that lets us live safely inside the motion of everything. Yet, even within that beauty, our own attempts to track time have stumbled. And once, We lost entire days just trying to correct for it. Part 10. The 11 days that disappeared from history. Imagine waking up one morning to find that 11 days of your life had simply vanished. Not lost, but completely erased from the calendar. That is exactly what happened in September of 1752, when people living in the British Empire went to bed on September 2nd and awoke on September 14th. 11 entire days were just gone. This did not happen through war or through some natural disaster, but through mathematics. This strange event was not magic or myth. It was the direct consequence of humanity's long and arduous struggle to measure something that seems deceptively simple: the true length of one rotation and one orbit of the Earth. The era of this error began centuries earlier with the Julian calendar, which was introduced by Julius Caesar in 46 BCE. Roman astronomers, guided by Sosigenes of Alexandria, had calculated that a year, the time it takes for one orbit of Earth around the Sun, lasted 365.25 days. To balance out that extra quarter of a day, they simply added a leap year every 4 years. It seemed like a perfect system. But over the centuries, that 0.25-day approximation introduced a hidden drift. The real tropical year, which is the time from one spring equinox to the next, is actually 365.24219 days. This is about 11 minutes shorter than the Julian calendar's value. Those 11 minutes per year built up, quietly and relentlessly, like sand piling up in an hourglass. After 128 years, the calendar was ahead of the seasons by one full day. After 1,500 years, it was nearly 10 days off. By the mid-1500s, the spring equinox, which is supposed to occur around March 21st, was actually happening on March 11th. The sun itself was out of sync with the human calendar. To the astronomers of the time, this was not just inconvenient, it was catastrophic. The timing of the equinox determines the timing of major religious festivals, agricultural planting schedules, and navigational charts. The skies no longer matched the dates that were written on parchment. So, in the year 1582, Pope Gregory XIII, acting on the advice of the Jesuit astronomer Christopher Clavius, ordered a global recalibration. The new Gregorian calendar would fix the drift by immediately skipping 10 days. Thus, in Catholic Europe, Thursday, the 4th of October, 1582, was immediately followed by Friday, October 15th. This correction instantly restored the calendar to its proper place with the seasons, but not everyone agreed to adopt it. Protestant nations, deeply suspicious of any papal authority, clung to the old, inaccurate Julian system. For nearly 2 centuries, Europe lived with 2 competing calendars. England and its colonies finally made the switch in 1752, by which time the Julian system was lagging 11 days behind. The British Parliament decreed that September 2nd would be followed by September 14th, erasing the accumulated error in one single stroke. The result was one of the strangest transitions in history. An entire week and a half was simply skipped. Legend says that angry mobs took to the streets, shouting, "Give us back our 11 days." While historians now believe these protests were likely exaggerated, the confusion and mistrust were very real. Contracts had to be rewritten. Birthdays shifted. Even George Washington ended up with 2 birthdays: February 11th, 1731, Julian, and February 22nd, 1732, Gregorian. But beneath all the social chaos lay a profound truth. Time, as we human beings record it, is not absolute. It is a collaboration between cosmic motion and human precision, and that precision must constantly evolve. NASA's Goddard Space Flight Center describes the Gregorian reform as a correction that restored harmony between human time and celestial time. It realigned our calendar with the Earth's actual orbit around the Sun, a process that would be confirmed with incredible accuracy centuries later by spacecraft measurements. Today, the Gregorian system remains the international standard. Its average year lasts 365.2425 days, which is only 26 seconds longer than the true tropical year. That means it will take over 3,300 years for our modern calendar to drift by even a single day. Still, even this extraordinary accuracy is not perfect. The Earth's rotation, as we know, is gradually slowing down due to tidal friction from the Moon. The length of a day increases by about 1.7 milliseconds per century. This means that over thousands of years, even our best timekeeping systems will require further adjustment. That is why organizations like the International Earth Rotation and Reference Systems Service, IERs, occasionally add leap seconds to Coordinated Universal Time, UTC. These microscopic corrections keep our atomic time synchronized with the planet's real, physical rotation. It is the exact same principle that once demanded the 11-day correction of 1752. Only now, we are measuring the discrepancy in fractions of a second. If we did not make those tiny adjustments, our clocks would eventually drift away from the Sun's position. The time displayed on every phone and satellite would gradually, but inevitably, lose its alignment with the actual sunrise and sunset. It is remarkable to think that our entire civilization, from agriculture to navigation to spaceflight, depends on our ability to measure the Earth's spin accurately. Astronomy, physics, and engineering all intersect at this single truth. Our planet is simultaneously a clock and a moving spacecraft. The European Space Agency, ESA, uses this principle every time it calculates orbital transfers. Every spacecraft launch window is timed not by the human calendar, but by the Earth's exact rotational and orbital position relative to the Sun. Even a 1-second discrepancy in timing can shift a probe's final trajectory by hundreds of kilometers. In that sense, the 11 days lost in 1752 were not wasted. They were the price of realignment. Humanity recalibrated its master clock to match the true heartbeat of the solar system. And that heartbeat can now be measured with exquisite precision thanks to atomic timekeeping. This is defined by the vibration of cesium-133 atoms, which oscillate at exactly 9,192,631,770 oscillations per second. We can measure time so precisely that even the gravitational differences between mountaintops and valleys register as measurable effects. Einstein predicted this phenomenon, gravitational time dilation, in his theory of general relativity. Experiments using atomic clocks have confirmed that clocks do run slightly faster at higher altitudes, where gravity is weaker. In the future, this precision will redefine not only how we keep time, but how we map the planet itself. From this perspective, the lost 11 days of 1752 are a powerful symbol of progress. They are proof that human understanding of time is always evolving, always refining itself to better match the natural, complex rhythms of the universe. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you. And yet, we have built systems to make sense of it anyway. Systems that can align calendars, predict eclipses, and send spacecraft billions of kilometers away with mathematical precision." When the British Empire erased those 11 days, it was not rewriting history. It was synchronizing with reality. And in doing so, it quietly joined a long legacy of countless astronomers, mathematicians, and engineers who have spent millennia ensuring that humanity stays in step with the cosmos. It is humbling to think that every date, every clock, and every schedule in your life exists because of this constant, ongoing recalibration. From the 11 missing days of the past to the leap seconds added by modern scientists, our timekeeping remains a moving target, forever chasing a planet that never stops turning. Carl Sagan once said, "We are like butterflies who flutter for a day and think it is forever." But the truth is, even during that brief flutter, the planet beneath us is adjusting, realigning, and correcting its measure of motion against the stars. So, when you look at your calendar, when you see a February 29th, or when you remember that 11 vanished days once realigned human civilization, know that this, too, is part of the same story. It is the story of a world in motion, measured by minds determined to keep pace with the heavens. And as this chapter closes, our journey through motion, time, and precision finds its quiet conclusion. It is a reminder that every tick of every clock, from ancient sundials to modern atomic oscillations, is a conversation between the Earth and the universe. If this quiet voyage through time and space has brought you even a moment of peace, I am truly grateful you have shared it here with me. A gentle like or a soft tap on the subscribe button is not just support. It is encouragement to keep exploring these sleeping worlds of science together. And if you would like, I would love to know where and when you are listening from. Your words, whether they are short or long, are like little stars that help guide the next journey. Until then, rest well, drift easy, and remember, even in stillness, we are always moving. I wish you a peaceful night, a deep sleep, and the gentlest of dreams beneath this vast moving universe.